yasas. Actually, my speech will be on analysis of wind catchers, decorative pools, and outlet opening combinations on the cooling of residential interiors. I carried out this research with a student of mine who is dealing with numerical simulation analysis, Mr. Anıl Berkatalar, so I have to say his name as well, mention his name. So my presentation will go through the following steps. I will first introduce the matter. I will start with the introduction by approaching the research topic from sustainable habitation and vernacular wisdom perspectives. Then I will introduce the residential building model, which is, for the time being, only tackled by means of numerical analysis, not experimentally yet. I will talk later about the computational methodology, although I have to admit at this point that I am an experimentalist, not a numericist. And assessment of numerical predictions will follow. And finally, I will conclude with some remarks and suggestions for future work. Actually, the earliest documented design of windmills, not wind catchers, but windmills, dates back to 1200 BC. In the Persian Peninsula, Persians used windmills for grinding grains during this period, about 3,000 years ago. In those days, wind catchers were vertical axis machines having sails made with bundles of reed or wood, and the grinding stone was attached to the vertical shaft, the end of the vertical shaft. So this is the planar view. This is the three-dimensional picture, and this is the real picture. I don't think this is an extremely ancient windmill. However, I think it's a reconstructed windmill based on the vernacular architectural documents. Well, it was not only the Persians who worked on the power of wind to make it usable for data purposes, but it was also the Egyptians. Actually, this is the only picture coming from the burial tomb of Neb Ammon, the pharaoh at that time, who lived at the 1300 BC. In Arabic, it's called Malkaf, which is actually the wind catcher itself. Here we see two triangular figures, and we assume that one of these triangles could be the opening mouth, the entrance mouth of the wind catcher, whereas the other one is the discharge mouth of the wind catcher. So this is the first picture, or the only picture we have coming from a burial tomb depicting a typical wind catcher. Now, coming towards our age, centuries after, we are able to observe a similar concept in the city of Yazd in Iran. These two pictures respectively show us the external and internal views of a very magnificent palace, Devlet Abad Palace. We see clearly a rather tall tower. Actually, this is the wind catcher itself. So it's somehow, when we look at the right-hand side figure, you see that this tower opens to the dome of the interior cupola. But there is one more thing. Maybe because of the beauty of the exterior view and the interior view, we don't see it immediately, but it's this pool over here. Okay? And there is a reason why the pool is there. This brings us to the goal of this research. Actually, the goal is to create a thermally comfortable interior space by the combination of the wind catcher and the decorative pool. We are using a numerical methodology to assess the use of cooling capability of an interior evaporative pool in conjunction with a wind catcher. These figures are not from the Evaporative Palace, the one that I showed you a minute ago, but they are both from Iran as well. During this methodology, we use two different parameters. First, we vary the wind speed. We use 4 meters per second and 6 meters per second wind speeds. And we also change the location of the outlet openings of a certain physical model, a building model, which I will show you in the next slide. Well, in the second slide. Okay, so I will skip this very quickly. It's just to give you a certain methodology. Actually, there are two distinct equations which are existing in the literature. Sorry. And the first one is the Asst equation. Actually, this equation gives us a WP, which is the evaporation rate in terms of kilograms per second. And the second equation is coming from a EinB2018, the German standards. And for 4 meters and 6 meters per second, these two equations give very similar results. Approximately 0.1 grams per second evaporation rate. The reason why we need these formulas is to embed them into the numerical analysis program. Okay? So, now I pass to the second slide, and here we see the model. We have a building which is 6 meters in width, 4 meters in height, and 8 meters in length. Upon that, on top of that building, we have a chimney-like structure, which is actually the wind catcher itself. It looks like a periscope, as you see. Inside the room, we have a 2 meter diameter pool, a shallow pool, and here are the 4 different locations of our outlet opening. Okay? So what we do here is to admit the 4 meter per second or 6 meter per second wind into this chimney and bring it to the interior and then discharge it from one of these slots. This picture at the bottom shows you the numerical or meshed version of the physical model. We were able to use hexagrid meshes, and the total number of mesh elements were about 1.5 million. So, at the beginning, what we did was to divide the domains into two, namely the external domain and the internal domain, which is the inside of the residential building. Then we solved the equations, the fluid motion equations, first at the exterior part, and then by having the inlet profile, velocity profile, then we started running the same type of computations, this time for the interior volume. If we haven't done that, that would be very difficult and time-consuming and costly to run the full computational domain, to solve the full computational domain. So that's why we divide it into two parts. So as soon as we have this velocity profile at the mouth of the wind catcher, then we start solving this domain here. Okay. Now, what about the conditions for the internal flow analysis? First of all, air enters at wind catcher's inlet with previously obtained velocity profile from the external solution. Air exits at obtained outlet gauge pressures from these slots. K-epsilon turbulence model was used because we observed that in the literature, this turbulence model is suggested for such type of solutions. Coupled algorithm with second uplink schemes, species transport model for evaporation rate, vapor mass, energy model were also used, and natural convection at the walls except the ground was accepted. The temperature of water in the pool was 26 degrees Celsius. The temperature of outside air was 35 centigrade degrees. The relative humidity of air was 30%. And the horizontal velocity above the pool for 4 meters per second was 14 centimeters per second. And likewise, horizontal velocity above the pool for 6 meters per second wind, the velocity was 20 centimeters per second. These were the boundary conditions. Now, you see 8 different pictures here, but don't worry, I'm going to explain them to you. Now, A, B, C, and D, they are there for different outlet openings. So this and this analyzes the case when the outlet opening is only 60 centimeters above the ground. But then the question is why we have two different pictures. Well, the first one is for 4 meters per second, and the second one is for 6 meters per second wind velocity. Likewise, here again 4 meters per second, 6 meters per second, but this time the outlet opening is 120 centimeters above the ground, 240 centimeters above the ground, and finally 330 centimeters above the ground. So now we want to know which one of these configurations will perform the best in terms of temperature decrease and in terms of relative humidity increase. Now, this picture shows a clearer, or gives us a clearer understanding. Once again, these are for 6 centimeters above the ground, 150 centimeters above the ground, 240 centimeters above the ground, and 330 centimeters above the ground cases. 4 and 6 meters per second wind velocities. Now, this shows us the temperature distribution at an average temperature distribution at 2 meters above the ground. So, what we are doing here is to cut a horizontal cross-section at 2 meters inside the room and look at the temperature distribution. These contours represent the cooler and warmer spaces in the room at 2 meters per second cross-section. Now, for 4 meters per second wind speed, the average temperature at 2 meters above the ground is 32.5 centigrade for outlet 4. It's this one. However, average temperature is 33.5 centigrade for outlet 1. These are for 4 meters per second. Well, when you look at the color codes, the outlet opening at 330 centimeters, that means case 4, performs better in terms of temperature reduction than the outlet opening at 60 centimeters above the ground. Okay? Now, if we pass to 6 meters per second wind speed case, it's these cases, the average temperature at 2 meters above the ground is 33 centigrade for outlet 4, it's this case. However, average temperature is 34 centigrade degree for outlet 1, that's 60 centimeters above the ground. Okay. Now, this time we see it from the side. Outlet 4, that means these two cases, reduces the temperature of the air inside the room to around 32 centigrade degree by aspirating up the relatively cold water vapor on the surface of the pool. Let's do not forget that the outside ambient temperature at the outside of the room, of the residential unit, was 35 degrees Celsius. So this means that we were able to decrease the temperature by about 3 centigrade degree by using a simple pool, shallow, simple decorative pool. Now, there is some interesting distributions here. Now that we all agree that for outlet 4 performs the best, let's look whether it performs the best for 6 meters per second or 4 meters per second. There we clearly see by looking at the colors that 4 meters per second wind velocity performs better than 6 meters per second wind velocity. This seems a little bit strange, but don't forget that for 4 meters per second wind velocity, the residence time inside the room is larger. So what the flow does is, after admittance into the wind catcher, the flow passes through this channel, then impinges somewhere here, then moves upwards and is discharged from the outlet opening. Okay? For 6 meters per second, the flow does not have sufficient time to pick up the moisture from the pool level surface. That's why it performs a little bit worse than the first case, 4 meters per second case. I'm not going to bore you with these graphs. I'm just going to jump into the conclusions. Velocity of air was between 25 centimeters per second and 60 centimeters per second. In each case, in each numerical predictions, at the average human height, and according to the standards, this is quite comfortable. For example, in primary schools, what we need is like 25 centimeters per second draft velocity to feel comfortable. And that's accomplished, achieved. Lower air velocity enables the room to cool down more efficiently. That means 4 meters per second velocity, wind velocity, enables the room to cool down more efficiently and increases more the relative humidity in the room. An inverse relationship between the temperature distribution and relative humidity exists. One more thing I have to mention, and then I will conclude. I forgot to say this, but in each of these pictures, we see that on the lateral walls, on the side walls, we have cooler flow. This is because the air which is admitted from this wind channel impinges on the axisymmetrical locations within the room. It also entrains the side air. So the side air being entrained towards the lower parts of the room, something has to replace this air, and this air then is replaced by the air which is climbing up the lateral walls. That means the locations closer to the side walls are cooled better than the locations at the axis of the room. And that's also very nice, because In Eastern living spaces, not today, but in the ancient times, the divans, the sitting spaces, were distributed along the side walls. Okay? And in the middle, there was this pool. So this is very nice because then the people who are sitting on the divans can feel a comfortable environment. So in that respect, this is the sign that the flow is nicely distributed or properly distributed within the room. So the last slide. I told you about the evaporation rates. They are quite suitable with the standards. They agree very well with the standards. Location of outlet is an important factor for cooling performance and in the air indoor quality. Average temperature at the middle section, 2 meters above the ground of the room, decreases about 2.5 to 3 centigrade degree with evaporation, and lower wind velocity plays more important role than higher wind velocity for cooling of the building. 4 meters per second wind speed provides more quality for air comfort with moisture, and it varies from 30% to 45% up to 1 meter. However, 6 meters per second wind speed enables increasing of relative humidity up to just 35%. The best outlet position was obtained as outlet 4, which is 330 centimeters above the ground. And combination of wind catcher and decorative pool provides approximately 3 centigrade degrees in average temperature and increases relative humidity up to 45%. One more thing, these type of combinations are also very important, very nice for manuscript collection rooms, because there we don't want low humidity. Because paper, by time, becomes brittle because of the dry air. So within the collections room, manuscript or library room, if we have a pool, it helps. Of course, it helps when the climate is arid and very hot. It may not help in Athens, it may not help in Istanbul, but if you go towards southeastern parts, to Iran, to Middle Eastern countries, away from the seashore, then it helps a lot. So that was my last words. Thank you very much for your attention.
Thank you very much. Are there any questions? Yes, please.
I'd like to ask you if you can measure any proportion between the wind culture and the existing openings of the building. As you do the glazing, appears the presence of high humidity.
I may have misunderstood you, but I forgot something. Thank you for reminding me. These things are only numerical predictions. And I told you that I admitted that I am an experimentalist. I have not run the predictions. My student did. However, my job will start soon because I am going to build a model, a small model, the same physical model, and I will put it inside a wind tunnel, and I will start measuring the relative humidity and the wind speed. We have I don't know if you are familiar, but we have in our laboratory a PIV measurement system, a particle tracking system, let's say, which gives us the velocity distribution within the room. Okay? That will follow in the second campaign, and I hope we find similar answers. Yeah, okay. But I don't know if I can answer your question. I mean, maybe you meant something else. Okay.
Yes,
Okay.
I see that you will...
We will continue and we will try to validate the results.
So next year.
I hope so. I hope so. Okay. Yes?
Any other question?
Yes, in the graph charts you showed us, the CFD graphs, you said that the best option was to have the outlet of 4 meters per second, 3.3 meters.
Yes.
And then the flow sticks to the wall, because this is what I saw in the graph.
Let me see. This one?
No, the other one, the section. One would expect that the flow would not be so close to the wall. I mean, yes.
Good point. However, maybe you don't see it, but here you have a separation panel. You see?
Yes, sir, that's 3.3 meters still. So
3.3 meters is here.
the outlet, where is the outlet?
This is the outlet.
No, I'm talking about the inlet of the air.
Inlet is here. It's about 8 meters.
Right. And then it goes to an outlet inside the room. Where it is? There.
It's here.
Okay. And there, the flow remains
Attached.
attached to the wall. Although it's 75 degrees inside, it's less. It doesn't separate from the wall. Because if you have 4 meters per second and 3.3 meters height coming onto you, this is far away from comfort standards. I heard what you said about the mean velocity of the air in the habitable zone being around
20 centimeters and 60 centimeters, yes.
no, 1.5 and 0.6 meters per second.
Yes, yes.
But the outlet, in the outlet,
Here.
there, it's 4 meters per second, right?
That's true. I cannot read the value here, but it should be now.
Because of continuity, it must be 4.
No, actually, the velocity of the speed is the velocity of the wind is 4 meters per second. Now I don't know. I cannot read what the velocity here is because it's entering a contraction. I don't think the velocity there is about 3 meters per second. It must be less than that.
Because if it was 3, then it wouldn't collate the wall, it wouldn't remain attached to the wall, and it's far away from standards.
It's true. I mean, I cannot read it. I wish I could read it here. Maybe I can read it from here.
But anyway, I think this is temperature measures.
Sorry, this is temperature, right?
Yes.
This is temperature. Yes, I'm sorry. This is not velocity distribution, sorry.
Still the temperature, since it's 35 degrees, and it's
35 degrees, it's true.
it's different. It should be a little more like a triangle close to the wall. I mean, the flow will be touch.
Yeah, a diffusion should take place, you said.
But you said before that there's a Bernoulli effect, of course, coming from the secondary air of the room.
Yes.
That's lessen the effect. Although this sounds very optimistic.
What sounds very optimistic? You mean the...
The flow will remain attached to the wall all the way down.
Yeah, but I don't think it's optimistic then. I mean, now I have to act opposite to what I say, but red means 35 degrees Celsius.
Yes.
So actually, if you stay here, then you are not comfortable.
Yes, I would expect that it will go even higher in the habitable zone.
Once again, these are numerical predictions. And let's see what happens when we obtain the experimental results.
Sure.
But thank you very much for your contribution.